Now we will understand what is parallel axis theorem. When do we define parallel axis theorem? Let us consider an example. I have a circular plate and whose moment of inertia about an axis which is passing through the center of mass is known to me. That let me represent it as ICM as given in the formula in this slide. ICM suffix Cm is defined as moment of inertia about the axis which is passing through center of mass. And now I would like to, for some particular reason, I need to find out what is the moment of inertia of another axis which is not passing through center of mass, but it is parallel to the axis which is passing through the center of mass. Then that can be written as I. Therefore, if I know the moment of inertia of a given planar body about the axis which is passing through the center of mass, I can always calculate moment of inertia of another axis which is parallel to the axis which is passing through the center of mass, can be written as I is equal to ICM plus the product of the total mass m and square of the distance between these two axes. That distance, if I denote it by d, then I is equal to, I is the moment of inertia about the particular axis to which I need to calculate. Therefore, I is equal to ICM plus m into d square. Now, let us go to the tabulate where the moment of inertia of a body about an axis, about any axis, is equal to the moment of inertia about a parallel axis which is passing through the center of mass of the body plus product of total mass and square of the distance between these two axes, where big M is the mass of the body and d is the distance between these two axes as represented in this particular figure. Now let us try to give proof for this parallel axis theorem. The moment of inertia about the center of mass, that is the point O in this particular figure in the right hand side, is given as summation of mass of the particle mi and distance, and the particle is at a distance r from the coordinate axis, where that is also passing through the center of mass. Now let us consider the blue dot, what is written as mi. The corresponding coordinates can be written as xi comma yi. The coordinates for the point whose mass is mi is xi comma yi. Therefore, in the first formula ICM, we have to look at the left hand side. ICM is equal to sum of mi ri square equals sum of, that can be written as ri square, can be written according to Pythagoras theorem as xi square plus yi square. Now, our aim is to find out moment of inertia about another point P, and let me treat the coordinates at point P as xi minus a comma yi minus b. Then according to that relation, for any at any point the moment of inertia of the axis which is passing through the point P can be written as ip, can be written as summation of mi into the coordinate squares, that is xi minus a whole square plus yi minus b whole square. That entire addition is multiplied by mi. Now we will separate these terms, that is equivalent to summation of mi into xi square plus yi square minus 2a into summation of mi xi minus 2b into summation of mi yi plus a square plus b square multiplied by summation of mi. Now the first term in the second line, that is summation of mi xi square plus yi square, is equivalent to ICM, that is moment of inertia about the center of mass. And second term can be written as minus 2a times summation of small mi over the entire distance can be replaced by bigger M, that is the total mass of the body, big M into xm xcm minus 2b into big M into ycm plus the last term a square plus b square from this figure. If you look at carefully at the right hand side, a square plus b square, again according to Pythagoras theorem, is equivalent to d square. Therefore, a square plus b square can be written as d square. Now, in the right hand side, I have moment of inertia at the center of the body minus second term and third term. What is xcm and what is ycm and what is the position A and what are the position B are the unknown things. Now, let us assume that what is xcm, since the origin of the entire coordinate system we have considered which is passing through the center of mass, therefore x center of mass comma y center of mass is equivalent to what is the origin coordinates 0 0. Therefore I can substitute 0 in case of xcm as well as ycm. Then the above equation turns out to be the moment of inertia about an axis which is passing through P is equivalent to ICM, that is moment of inertia about the center of mass, plus bigger M, total mass of the body, multiplied by square of the distance between these two axes. Hence we have proved this theorem. Now there is an alternative method to give the proof for the same. Why I have included this slide is that this is how we have given in the notes. You can follow one of the methods, whichever is convenient for you. Now let us consider a body whose mass is m, whose center of gravity is at g, and the g is the point where the line or a vertical line, you can see that CD is passing through that, and let the body rotate about an axis AB. Now this is the new axis AB, where that is the moment of inertia I need to find out. Therefore, that moment of inertia is I, and let I be the moment of inertia about the AB axis, and CD is another axis which is passing through the center of mass G. Therefore, that moment of inertia is represented as Ig suffix G, and let R be the distance between these two axes. Now I need to find out what is the value of I. Now let us consider a point P which is having mass m and it is at a distance x from the axis CD. That is the point G. From G, x is the distance at which the given particle we have considered. Therefore, the moment of inertia of the particle of mass m about AB that is defined as I is, one can write that moment of inertia as m, that is the particle's mass, that is particle which is located at point P, that particle mass is m, and multiplied by the distance between the particle with respect to the axis AB is r plus x according to this diagram, r plus x whole square. Now let us try to rewrite this equation once again. That is moment of inertia of the body about AB, I is equal to summation of m into r plus x whole square, which is equivalent to, we'll go to the next step where r plus x whole square can be written as we know that a plus b whole square can be written as r square plus x square plus 2rx. Now we will separate the terms. Therefore, first term becomes summation of mr square, small mr square, and second term is summation of small m and x square, and the third term in the equation is summation of 2mr into x. Now, as we know that summation of m gives the total mass of the object, therefore the small m is replaced along with the summation term as big M, and first term becomes big M r square, and second term we will retain as it is, and we will try to take out this r from the third term, and then that becomes 2r into summation of mx. Now as it is written over there, summation of small m is the big M, where the mass of the body, and summation of mx square, if you consider that mx square representing the moment of inertia of the body about an axis which is passing through the center of mass. Therefore, that can be written as Ig. It gives the moment of inertia of the body about the axis CD, which is passing through the gravity. And the last term, where we have summation of mx, gives the algebraic sum of the moments of different particles about the axis CD, which is passing through G. Now, please remember that whenever we consider moments of different particles about that axis which is passing through G, that always somehow the summation becomes 0. Therefore, the above equation turns out to be the last term. The summation of mx becomes 0, therefore we have to neglect the last term. Therefore, finally we got I is equal to Ig plus mr square. Hence, we have proved this relation. Now we'll go to perpendicular axis theorem. Why do we worry about perpendicular axis theorem? Because it is used to determine moment of inertia of a rigid body that lies entirely within the plane. Therefore, whenever we define perpendicular axis theorem, we should always remember that we are always talking about a flat disk, a rectangular plate, or circular disk. Therefore, how do we define it? Let us go. For a planar object, the moment of inertia about an axis perpendicular to the plane is the sum of the moments of inertia about two perpendicular axes passing through the same point in the plane of the object. Now let us closely look at the given figure, where I need to calculate what is the moment of inertia about the axis which is passing perpendicular to the plane of the body, that is Iz, that is given in the z direction. That can be written as that Iz can be written as Ix plus Iy. What is Ix here? Ix is the moment of inertia of the same body but along the axis which is lying along the x direction, and similarly Iy representing the moment of inertia of the same body whose rotation is happening along the y-axis. This is how we define perpendicular axis theorem. Now we will go to proof of the same thing. Now let us please look at the same blue spot in the given figure, where the particle whose mass mi is identified, and let us try to write the formula for moment of inertia of this entire body which is rotating along the z-axis. Therefore, Iz can be written as summation of mi into Ri square as given over there. Now, when the given particle whose mass is mi and it is at a distance Ri, then we can always write R in terms of x and y values. According to the same formula, we can write that mi Ri can be Ri square can be written as summation of xi square plus yi square. Therefore, that is how we get the second line in these equations. And we are going to separate these two terms in the third row. Therefore, that becomes summation of mi xi square plus summation of mi yi square. Now, as we define, we have already familiar with this moment of inertia formula. Summation of mi xi square is moment of inertia along the x-axis, and summation of mi yi square is the moment of inertia along the y-axis. Therefore, Iz is equal to Ix plus Iy. And we are also going to discuss about radius of gyration. How do we define radius of gyration? Let us look at this statement. Radius of gyration of a body for a given rotational axis is equal to the distance k from this axis, such that when k square is multiplied with the total mass of the body will give the moment of inertia of the body about that axis. Please remember that for a given object, radius of gyration differs for different axis of rotation. As moment of inertia itself differs for a given object, here also radius of gyration also changes. Now consider a body of mass m with moment of inertia I is equal to summation of mi ri square about a chosen axis. Then radius of gyration can be written as I is equal to big M, that is the total mass multiplied by k square. Therefore, radius of gyration can be written as k is equal to square root of the ratio of moment of inertia to its total mass. Thank you. We will discuss about other concepts in the next video. Thank you.